This video is part of a series on the xv6 operating system kernel. In this video, I'm going to go over the main function and talk about the startup procedure. But first, I'll briefly discuss the organization of the files that make up the xv6 system. I'll end by quickly covering the files types.h, defs.h, and param.h. Let's begin with the files that are included with the xv6 system. These files are organized into three directories: kernel, user, and a folder called makefilesystem, mkfs. The kernel directory contains a bunch of .c and .h C source code files, as well as a couple of .s assembly code files. These are all compiled and linked together to produce the executable kernel. The user directory contains the programs that will run in user mode, such as the shell, cat, echo, ls, and so on. It also includes some files for testing the kernel, some library stuff, and a makefile. The mkfs directory contains a program used to build the initial file system and create the disk image. We also have a README file, a license file, and a makefile to compile everything. Here's a list of all the files in the kernel directory as of this date. We see our 4 assembly code files, all fairly short. Then we have a bunch of .h include files and a bunch of C source code files. All these get compiled and linked together into a single executable file. This kernel.ld file is a linker script that tells the linker how to do that and where in memory to put things. And here are the files in the user directory. First, we see it contains the shell program and the command line tools like cat, echo, and so on. init.c is the initial program that becomes the very first process and gets everything started. Then we've got some useful functions that get included in every user program. This would include functions that you're used to, such as string length and printf and malloc. Normally these would come from a library, but we just include all this code in every user program. usys.s contains a bit of assembly code that will get included in every user program. It's constructed automatically by this Perl script called usys.pl. user.ld is another linker script that controls the linking of all the user programs. Then we've got a bunch of programs that will test the xv6 kernel for correctness. We've also got a Python script here that will run the test suite. And finally, we've got a makefile, README, and a license file. Next, let's ask what happens after power on or hardware reset. Basically, QEMU just loads the executable file into memory and jumps to an address called the entry point. There's an assembly code file called entry.s, and it contains the entry point. The first instruction to be executed is in this entry.s file. Once the kernel begins execution, the code in entry gets things set up so we can execute C code. Now, in order to execute C code, we have to have a valid stack. We need a stack in order to call functions. The stack is controlled by a register called SP, the stack pointer register. The code in entry.s will initialize the SP stack pointer register, and then it calls a function called start, which is written in C. Now, there are a bunch of cores, and they're all sharing memory, so they'll need to use different areas for their stacks. The code running in entry.s will look to see which core it's running on, and it'll initialize SP differently for each core, so that each core is using a different memory area for its stack. This file is just half a dozen instructions, and all it does is initialize the stack pointer and transfer control to start, which is a C function. Every RISC-V computer begins execution in machine mode. However, the kernel will run entirely in supervisor mode. The start function will perform some hardware initialization which has to be done in machine mode, and then it'll switch to supervisor mode and call the main function. So start will get the hardware configured as it needs to be, and then switch into supervisor mode. Main and the entire kernel will run in supervisor mode, with user mode being used for user programs. Main will never return. We'll never come back here and never execute in machine mode again after this. Keep in mind that xv6 runs on a multi-core computer, so the same thing will be happening on all 8 cores simultaneously. So all 8 cores will begin executing in entry, then in start, and then they'll all call main independently and concurrently. Okay, now let's take a look at the main function. This comes from a file called main.c, and it starts with some includes. I'll go over a couple of these includes in a second. Notice that we don't see things like studio.h or string.h or the standard library. In all of the kernel code files, we only include files that are part of the xv6 system. All these files are part of xv6 and were included in that list of files I showed a bit earlier. Main has 2 phases. First, it does a bunch of initialization, and then it invokes the scheduler function down here. The scheduler function never returns, so main never returns. Keep in mind that this function is being executed simultaneously on all 8 cores. Some initialization only needs to be done just once. For example, various data structures have to be initialized and set up, and this only needs to be done one time by one core. Other initialization has to be done on every core. For some things, every core needs to do initialization. The way main works is it first asks whether it's running on core 0. That's this big if statement. If this is core 0, then we execute this block of code here. This does the initialization that needs to be done just once. Otherwise, on all the other cores, we do the else statements down here. CPU ID is a short little function that just returns an integer indicating which core we're running on. It returns a number between 0 and 7 to indicate which core, or we can say which CPU we're running on. You'll see this little CPU ID function used in quite a lot of places throughout xv6. 3 things have to be done on every core. They are kvm init heart, trap init heart, and plick init heart. Heart indicates that they are per core initialization. So you see these 3 things, kvm init heart, trap init heart, and plick init heart, being done on core 0 as well as the other 7 cores in the else statements. So what exactly does core 0 do? It begins by printing out this message that the kernel is booting. This printf is not the function that you're used to that sends characters to a file or to a pipe or something like that. Remember, in a kernel, we have to provide implementations for every function we use. We can't rely on other software. The code for the kernel's version of printf is in an xv6 file called, appropriately, printf.c. So how does our version of printf work? For output, the kernel relies on something called a console, which is just the UART device. Console is an old term that predates terminals, which of course predates screens and windows. Think of an old IBM mainframe computer that had a single so-called console terminal sitting in front of its gigantic control panel. The console is where all kernel messages will go. So printf sends characters to the console, which in our case is just the UART device. But before we can print anything, we have to initialize the console. And we also have to initialize a lock associated with the printf subsystem, and we do that here just before we print anything. Then we have to do a bunch of other initialization. For example, here we initialize the free list of pages, and here we initialize the kernel's page table, And here we set up the array that contains all the process structures. We have to initialize all the data structures before we can start the scheduling algorithm and begin executing user programs. Right now, let's not worry about exactly what all these functions do. Core 0 needs to make the other cores wait until all this initialization is done. Let's see how it does that. Up here, we've got a variable called started, which is just a Boolean flag. It's initialized to 0, and it'll get set to 1 after the core 0 initialization has been completed. The static keyword means that this variable will be local just to this file. So started is a private variable that's only used here and nowhere else. Volatile is a special keyword that instructs the C compiler to always go to memory whenever we read or update this variable. Normally the compiler will try to optimize things and it might put started into a register. We do not want that to happen. It needs to go to shared memory so the other cores will be able to see it. So core 0 will do all the initialization, and when it is complete, it will set started to 1. All the other cores will be stuck in this loop here, waiting for started to get set to 1 by core 0. Core 0 will do the initializations and then set started to 1 while the other cores are stuck in this tight loop waiting for that. Eventually, after core 0 changes it to 1, the other cores will see that and then will proceed to do their initialization. The first thing they do is print a message saying that this core, that heart, whatever, is starting. And here we see that CPU ID function again. By the way, all the code I'm showing you is copied directly without any changes from the Git repository, and it's current as of the end of 2025. The only thing I've done is to reformat it in a couple of places to make everything fit on the page nicely. And I've manually added some boldfacing in order to make it easier to read. And I tend to boldface function names in particular, but apparently I forgot to boldface CPU ID here. Remember that printf lock that I mentioned? Well, that makes sure that each of these messages is printed in its entirety without interruption. It makes sure that we don't get all the individual characters mixed together, interleaved together in a jumble, which would be hard to read. What about this synchronize stuff here? What's going on here and down here? Normally the compiler will optimize to the best of its ability, and that could include moving things around and reordering statements. For example, the compiler might think that there's no reason it can't perform this assignment statement at any point up here. After all, it's purely local, so it can't be used in any of these other functions, so it might move it upward. And there's also instruction pipelining. Normally, the compiler and hardware won't reorder instructions if it might change the program's behavior. But in this case, with other cores, they can't see the connections, and they might reorder instructions. And obviously, we can't allow that. Started must not be set to 1 until after all these functions have finished. Synchronize is a bit of compiler magic. It's not really a function. There is no actual code for this function. Instead, the compiler recognizes it and inserts special machine code instructions directly. Synchronize is a so-called barrier. It tells the compiler and hardware, don't move stuff around. In particular, it requires that it must complete everything that occurs before the barrier first, and it must not begin operations that appear after the barrier until that barrier has been reached. Barriers are also called fences. They force everything on one side of the fence to be done and completed before anything on the other side of the fence is begun. Complete all the initialization first, then, and only then, after all of that is complete, set started to 1. Down here, the synchronize fence forces the compiler not to start the per core initialization until after this loop terminates. Finally, after both core 0 and the other cores complete initialization, each core goes into the scheduler function and starts executing user processes, and we never return to main. So that's it for the main.c file. Now let's look at the file named types.h. You're probably familiar with the shorthand names or something similar for the various integer types. On the RISC-V architecture we're using, the int type is 32 bits, even though this is a 64-bit architecture. That's the way it is on 64-bit architectures, with short for 16 bits and long for 64 bits. For example, uint64 is an unsigned 64-bit number. For all addresses and pointers and so on, xv6 uses the uint64 type quite heavily. Just plain int is also used heavily for counters and so on. Type names like uint64_t are more standardized, but xv6 uses these names. We've also got this definition, which is used in only one place, and in my mind, it's completely unnecessary, so let's just ignore it. Now let's take a look at the file named param.h. It contains a bunch of constants that are used all over the place. These are hard-coded into the kernel, so if you want to change any of them, you've got to recompile everything. I've already mentioned that we have an array of 64 process structures. This constant nproc is the size of that array, namely 64. This constant, nCPU, is the number of cores, and it's set to 8. Then we have things like the maximum number of open files per process and the maximum number of open files in total. We've got the maximum number of inodes open at once. This is the maximum number of devices we can support, although we only have 2 devices. This is the device which contains the file system, which is device 1, the disk device. Maxarg is the maximum number of command line arguments that can be supplied to a user program during an exec operation. Maxop blocks, log blocks, and nbuff concern the disk and file subsystems. FS size is the total size of the disk's file system. It's not actually used in the kernel, but it's used by that other program that builds the initial file system, MKFS, the Make File System program that initializes the disk image file. Maxpath is the maximum number of characters in any path name. And here's user stack, which is the number of stack pages to put in each virtual address space, which is only 1. Finally, I want to look at a file called defs.h. This is included in all the .c files, and it pre-declares a bunch of names that are defined in other places, so the compiler will recognize these names when it encounters them and not complain about undefined symbols and so on. Here are the names of the structures: buff, context, file, inode, pipe, proc. That's the structure that represents a process. Spin lock and sleep lock for our 2 different kinds of locks, and stat and superblock. Then we have a bunch of function prototypes. For example, the file console.c defines these 3 functions. This is so we can call and use these functions from other files. So we've got all these functions listed, and they're grouped by file, by the file in which the function is actually defined. And skipping past all these, at the very bottom we have a preprocessor macro called nlm, which computes the number of elements in an array. This is a macro function. It takes 1 argument, which is the name of an array variable. This function just computes the number of elements in that array, and it does this by dividing the size of the whole array by the size of 1 element, namely the first element. Both these size of expressions can be evaluated statically at compile time, so the resulting number is actually a compile time constant. I suppose whenever you need to know the size of an array, you could just look back at the definition of the array itself and use whatever constant was used in the array definition. But in-elem is much simpler and less error prone. For example, in-elem is used for a bunch of for loops that run through various arrays. By using this macro, whenever you change the size of some array, you don't have to go through all the code and change a bunch of for loops all over the place. If you've used in-elem, you don't need to change anything beyond the array definition itself. Plus, using this probably makes the code a bit clearer, and since it's a macro function, it doesn't incur any execution penalty. Okay, that's it for this video. Thanks for watching. I'll see you in the next video.